I'm Nick.
And I'm Katerina, and we'll be talking about visualizing the impact of adversarial attacks on perception in convolutional neural networks.
Convolutional neural networks are a really powerful tool that have really taken over the world, and they're used for everything from uh, classifying pictures of animals to self-driving. And they are particularly vulnerable to certain types of attacks that can cause misclassification, and that's really dangerous because you don't want your car driving through an intersection.
So, current approaches at trying to figure out how to better understand adversarial attacks look at the internal representation of how the model changes, but they don't look at what the network thinks that it's saying after the attack, which is what we're aiming to do. And we're hoping that in this way we can better understand how adversarial attacks alter image classification for these convolutional neural networks, and eventually hope that it will help us to build models that are resistant to attack.
So our general workflow is as follows. We use a pre-trained convolutional neural network that's publicly available and a publicly available image data set. We take that image set and create adversarial images that result in misclassification. We put them both through the pre-trained model, and we train an upsampling model to recreate the original image. And then we're going to analyze the recreated images.
So our results basically showed that almost all of the images were incorrectly classified. As you can see, there was only 294 that were correctly classified. However, most of them are close in their semantic space, even when they are misclassified. For example, the correct class is toy poodle, and instead it's predicting it to be a standard poodle. And you can see this in this little results figure that more purple is more semantically similar, and more green means it's more further apart.
So qualitatively, we really saw three main ways that the network, that these adversarial images were causing the network to malfunction. The first way is what we already talked about. So these trivial misclassifications that sort of result from very minor changes that don't actually change the meaning of the network classification. So toy poodle to standard poodle. We also saw, like on the previous slide, changes in classification that appeared to be based on background exchange. So this is a relatively well-known phenomenon where camels can be associated with the desert or cows with a field, and so the classifier is using the background to predict the label, not the actual subject. And we think that that's what's happening in some of these where we had a an animal get misclassified as a puzzle. And we saw in the reconstructed image a background exchange. The last one is perhaps the most concerning, and it's this targeted introduction of removal or addition of pixels at a region of interest. You can see on the bottom row, this goldfish ends up being misclassified as a hamster, and the major perturbation appears to be in the middle between sort of the two orange blobs, and that isn't present in the reconstruction of the original image. Um, and so this is, but these are the vast minority of cases. And so for future directions, there is some recent literature looking at more specifically at misclassifications that result in semantic changes. And there's also some intriguing work to be done looking at autoencoders. So autoencoders are more explicitly designed to recreate the input data, and these tend to be more resistant to adversarial attacks. And there's a lot of work that needs to be done to understand why that's the case.
Thank you.